Adam is a senior project manager with geospatial services for Ayres Associates. Adam has consulted worldwide on GIS department best practices and workflows and received an international Esri Special Achievement in GIS Award. Adam is past president of WLA, currently chair of the Wisconsin Land Information Council and a board member of the Esri Wisconsin User Group. He's joined today by Tyler. Tyler is a geospatial project manager for Ayres. He's worked in the federal and state agency sectors where he has more than 10 years of experience with resource inventory and monitoring programs, working side by side with federal, state, county, and private sector partners. His focus as a remote sensing specialist has included object-based image analysis, wetland flora and fauna, hydrography, aerial photography, and LiDAR. Adam, I'll let you guys take it away.
Excellent. Thank you, Jim. Can you hear me?
Yes, go for it.
Right. Well, I know many of you know me. I appreciate the introduction. One of the reasons why I started working with Ayres is the excitement of being able to play with big data, but it was an early frustration of mine to realize how difficult it is for clients to use when you turn around these big data sets. The last thing that we want to see at Ayres is having our clients get data on a hard drive and only seeing one or two people using this base data that is so important to so many different departments. So today we're going to talk a little bit about what you can do to do more with that LiDAR data that may not be as important to the GISer in the room, but very important to planning and zoning, conservation, and other departments. I'm just trying to get my slides to go. So what is LiDAR? That's what I'm going to start off with. Then we're going to talk about why is it important. I want to talk about what else can we do with it. So today I'm going to hit on a real high level, building slope models, depression mapping, erosion, looking at building heights. And then we're going to do a bit of a deep dive segueing into what Andrew just talked about in elevation derived hydrography. So what is LiDAR? Most of you know what it is, but for those of you that don't, LiDAR stands for light detection and ranging. It works like radar or sonar, but in this case, it uses light pulses. And for the purposes of this presentation, we're talking about wide area collection off of a fixed wing aircraft. We want to talk about wide area data analysis, and that's the way this is collected. So what happens is you have this LiDAR system, this laser system that's attached to the bottom of a plane. It's going to shoot down laser pulses, and every one of those pulses of light is going to hit objects. That could be part of a tree, a picnic bench, and the ground. Everything that it hits, that light reflects, and it gets back up to the plane, and that creates this XYZ measurement for every one of those reflections across the project area. And when you collect millions or even billions of those points across the project, you start to get a really high grade surface, and you can pull out all sorts of other features from that data set. Because you get these wide area, high grade data sets, LiDAR data really started its use in government infrastructure in the creation of flood risk management and the FEMA floodplain maps that I think Jennifer had asked a question about in the previous presentation. But it also gets used for infrastructure management. You can map corridors and utilities to a very high degree with LiDAR data sets. It's used in construction management. I have dirt here, I'm going to move it over here, and I want to assess, did I achieve what I wanted to do? It's heavily used in natural resources conservation. That could be from a forestry aspect. It could be for wetland delineation projects, which you've actually seen some other presentations here at WLA. It gets used in agriculture. It's critically important for understanding where is water coming from, where is it going to go in terms of where do I need to add water, where should I add pesticides. That gets taken to a whole nother level when you're talking about precision agriculture and farming. We want to use LiDAR data for water supply studies. When we do projects out west, we're very often looking at how can we retain more water and use that over the course of the year. Here in the Midwest, where we have an absolute ton of water, it's more about where is this water, where is it going to go, and what are we going to do with all of it? And it's getting used in water quality studies. Where are we going to have these recharge zones for our natural water tables? Wildfire management, planning and response. All in all, basically every national study pinpoints LiDAR as one of the big data sets with the highest return on investment. The last version of this report said this was a 5-to-1 ratio. So every dollar that is spent on LiDAR data brings back $5 in return when it's actually being used for the purposes it should be. Here at Ayres, we produce a lot of other data sets in order to help our clients utilize this data a little more easily. We have the processing power to do that. Many times we're looking at trying to have improved hydro mapping, and that we're going to cover at the end of this presentation. We're using it to map 2D buildings, even 3D buildings when we've got high enough density. We're mapping our tree canopy polygons to understand green infrastructure in a community. We obviously still create 1-foot contours. That gets used in a lot of CAD environments where people have a difficult time using LAS point clouds. We're collecting county and region-wide culvert inventories with this data. We're mapping closed depressions. Those closed depressions can get used for water quality studies, planning and zoning. We're doing erosion susceptibility mapping. We're looking at slope analysis, zoning analysis, and we're mapping lots and lots of assets with the LiDAR data itself. And this is all stuff that if you have LiDAR data in your base map, you should be using it for. So just touching on how we would create some of these data sets that may be useful and why, we create slope ranges for clients. There's a lot of ordinances around slopes. For example, if we're looking at where and how you apply manure, slope has a big part to do with it. And a lot of that has to do with thinking about runoff. If you have high degrees of grade, you're going to get more runoff in the case of a precipitation event. Are we looking at a 6% grade, a 12% grade, or higher? Can I do that? In the same regard, we may be looking at construction ordinances along shoreland. So how are we going to find our slopes? Well, you're going to start off with your DEM. We're going to process that DEM in order to try to find slopes. And then we're going to create these categories of slopes and then analyze that in order to find these 6%, 12% grade areas, as in the previous example for the ordinance. And then I can compare that against my zoning, or I can compare that against my parcels to see if this application can be applied, or is this going to be an area of concern. For closed depressions, again, we've got laws and ordinances around what you can and can't do around these closed depressions, but it's critical to understand where are they, how big are they. Here we're many times going to be finding a closed depression. You're going to have construction issues where if water doesn't have anywhere to go and you place a building within a closed depression, it's going to have a lot of flooding issues. But you're also going to have water quality situations where if you have this natural depression in the surface of the earth and it rains, that's going to fill with water. And it just makes sense that that's going to be a potential recharge for your local aquifer and therefore your local drinking water. So we really need to understand where are these. So we're going to want to be able to create our depressions. We're going to want to have the boundaries for easy analysis of this. And if possible, we also want to identify where are the low points of those depressions. That would likely be a sinkhole or a natural recharge point. So in order to do this, I need a DEM, and then I also want my culvert inventory. Culvert inventory needs to have a real culvert. It should be running from inlet to outlet, as you can see on the left image here. But we want to take that line. It needs to be a 3D line. We're going to burn that into the DEM that would be supplied, say, with a typical 3-depth USGS project. We're going to burn that in order to create what's called a hydro-enforced DEM that means that we're removing this digital dam from the surface of the earth so that water can flow through a road because there's a culvert there. If you don't do this, the water's gonna impound on one side of the road until it crests, but that's not how water actually flows. We need to burn in that culvert to the DEM to create a water model. So you're going to find these depressions, and then we want to fill them. So you want to fill all these depressions until that water would crest out of that depression. That's how we know where the boundary of each depression is. We're going to analyze this over an entire project area. And what we end up with is a series of depressions across the landscape. And we can find the boundaries of them, as you see here on the map. But we also want to identify the low points. So we run a series of algorithms in order to try to find that lowest value. You can see that here and above sea level. So we convert this over to a depth, and away we go. We also do erosion vulnerability. What we do is we actually use the tools that the Wisconsin DNR had produced. So these are the eval tools. They are GIS-based tools in order to evaluate erosion susceptibility across the landscape. Requires several inputs, but most of which you're going to have ready access to, as LiDAR exists across the state of Wisconsin. So you need that high quality LiDAR data. The piece you may need to build is going to be that culvert inventory. We want to make sure over the area of our project, we're going to have the USDA soil survey. We're going to want to bring in our weather data. Precipitation has a large part to do with potential erosion, obviously. And we also want to understand our crop rotation. Our outputs from this are going to be the stream power index, soil loss, and erosion vulnerability index. So you can get these tools from the DNR. It's a fairly large list of complex tools. You can run that across the Huck watersheds that we were just talking about in the last presentation. So one of the first data sets you're going to be creating with your precipitation and your DEMs is going to be your stream power index. You can see where these streams are across this agricultural field. Now, obviously, these are not permanent streams. These are going to be a stream that is there after a rain event. We're going to run the next set of tools, and that's going to produce a potential soil loss. And you can see how the two correlate with one another here. Going to run a few more tools, understand our crop rotation, and eventually you end up with your erosion vulnerability index across an entire project area. And the last data sets I'm going to talk about creating here today are going to be understanding my building heights across the project area, typically a county. So again, here we've got various ordinances that can be in place. From a shoreland standpoint, you may have an ordinance that either says a maximum height of a building from a water body, or it may be an ordinance that has all to do with the lowest point of a building along a shoreland or other similar ordinance. Another common one is going to be looking at your airport protection ordinances, trying to find features above the surface of the earth that are too high for regulations by the FAA. And LiDAR data is the best tool to be able to run area-wide analysis quickly. So how do we do it? We're going to want to locate our buildings. So we get our building footprints. We run an analysis across the DEMs in order to try to find the lowest point around that DEM on that building. Similarly, we can take our classified LiDAR data where we have buildings, run an analysis against that in order to find the highest point of each building. So now we've got those 2 points, our highest and our lowest point. We have that on top of our building footprint, and then we can run a simple point and polygon analysis in order to attach that to our footprints in case we want to have that attached to the GIS. So pretty straightforward. With that, I'm going to hand this over to elevation derived hydrography with Tyler.
Thank you, Adam. Can everybody hear me all right? Adam, can everyone hear me?
Yep, sounds great.
All right, wonderful. So I'll just kind of dive in depth to one of the hot topics. Obviously, we've seen some other presentations on deriving hydrography, and I'm just going to be giving an overview of what type of products go into deriving hydrography and what you can pull out and some of the various methods that you can go down. But for the project purpose that I'm going to describe here is basically we want to be updating hydrography for the NHD or the DNR 24K stream and river centerline data sets. And we can do that utilizing new 3-depth LiDAR DEMs. And we can assess digital dams across the landscape and try to reproduce the streams as best as possible. And typically we know that most of the current 24K stream and river centerline inventories are derived from USGS topo quad maps, a lot of them from the 1960s. And you can see in the upper right image that it's, oftentimes they don't line up with reality where water is flowing on the landscape today. And so we'll dive into some other products later on here, but below here we do have some DEMs, some LiDAR DEMs, and then some culverts burned into that DEM, and then a version of the hydrologic position index, which helps users' eyes accentuate between convex and concave features across a landscape. And that's that red yellow image in the lower right there. And we'll be seeing more of that as we go. And so, like I said, here we have that HPI hydrologic position index. We can see, obviously the user's eye can see where water is flowing along the landscape. We have rivers and streams, and we have, a 2-lane road there, some county roads, maybe a railroad there. And so now when we overlay the DNR or NHD 24K waters, we can see that the streamlines do not accurately represent the meander bands, or some of the data sets, some of those rivers aren't even incorporated into the current data sets. And so what we can do is we can use the DEMs, the LiDAR DEMs, to enforce the culverts across the correct flow paths, and we can update the current inventories. We can replicate the current data, but much better. But our analysis, or any hydrologic analysis, really can go beyond what the current 24K data contain, and we can incorporate other more detailed culvert inventories to derive much more meaningful, complete water course data sets. And now, most of the methods, we've kind of hit on this earlier, but we take culvert inventories that are produced from a stereo imagery and LiDAR data sets. Multiple data sets go into the culvert inventories, and then we can apply those to the DEMs to create a hydro-modified DEM. And then we can run stream analysis tools. Now there are over 300 tools in ArcHydro for people to explore. But some of the main key ones that we talk about are flow directions, contributing areas, and stream definitions by thresholds. Now here we have an example of a county in Wisconsin, Calumet County. This county we recently collected culverts on, and Ayres spent quite a bit of time with a lot of county roads and farm approaches, farm driveways and things, and capturing a lot of culverts over the landscape. And this was by far one of the most per square mile that we've collected, over 15,572 culverts. This was a great data set to explore some of these tools on. And so here we have watershed DEM clipped out and buffered within the Calumet County borders, and we're just sort of overlaying, there's all the culverts, and without even a road vector data set on here, we can pretty much relatively see the roads, where all the county roads are, just by the culvert points. And here we have a zoomed in location of a farm field approach with a a river or a creek running through a culvert on the road. And in the imagery, you know, that piece of water is barely discernible from the, you know, the imagery. But the orange lines are where we've inventoried culverts and applied the culvert modification, hydro modification to the DEM. And so we can see in the DEM where we're applying, and then we can see in the lower middle DEM image that the resulting stream path that correctly flows, accumulates water and flows through that culvert in the center. This is the entire watershed, plus a little bit buffer. This is just some test data that we're running on different watersheds to see how they're applying with different culverts and different thresholds. Now, this one is the most accurately representative of modeling the DNR 24K or NHD 24K layers. Now, you know, we talked a lot about thresholds. Where do you set thresholds? This image here, obviously not all these lines, these vectors in this image are streams. You know, not every depression along the landscape is a stream or river. You know, they may accumulate water in a high water event, a 1 to 500 year flood or something like that, or just, you know, in the spring runoff, they may drain water away from a field, but they're not necessarily rivers or streams. And so when you initially run your stream reach vector analysis, you may underestimate or overestimate your contributing area thresholds. And so you need to alternate these thresholds given the terrain and the environment and the inputs that you have going into that. So there's a lot of complex factors that you need to analyze in order to produce a meaningful product throughout the landscape. It's also important to note that these vectors are going to have 3D elevation data attached to each vertex, so they will be a 3D deliverable then. Now, again, you know, the specific needs of the project would just be to update the 24K lines. That's what we're seeing here in green. And if we use our analysis to reproduce the 24K and just go a little bit beyond that, you know, we can clearly reproduce that, capturing more accurate meander bends and just a better representation of concentrated flow across the landscape. Now, it's also a very important note to say that, you know, stream is a dynamic feature. You know, who's to say that those USGS 24K lines weren't accurate back in 1960, right? Streams move, they meander, and every time there's a high flood water event or anytime there is a new LiDAR collect, it would be advantageous to update these streamlines. You know, and the first go around may be the most effort put into, but every time there's a subsequent LiDAR collect, you can continue to just update areas that of known concern or areas of erosion or deposition or management areas that are needed the updated line work for. And just as some examples, you know, here's a river in a forested area in the North Woods back in 1991. We have some change to 2003, you know, 12 years. Obviously, the point bars are a little farther extended, and we have some braiding downstream. Don't have too much change between 2003 and 2008. Just a little bit more vegetation growing on those point bars. But then in 2013, we see a pretty big change from where the braiding was in the center. You know, and that's because in this area, there was actually a flood in 2012 that really took out a lot of meander bends, extended them, and pushed a lot of sediment downstream. And here you can obviously see that you know, the current inventories and the LiDAR 24K elevation derived streamlines, you know, they don't line up, but one is more accurate given the, you know, when the LiDAR was collected, when the most recent elevation data has been available for that area. And again, anytime there is a significant water event and a new LiDAR collect is available, it would be advantageous to update any hydrography in the area. And now, why is this so important? Well, streams and rivers are at the bottom of this pyramid that we're showing here. And this is a function-based framework for stream assessment and restoration projects, habitat projects. This was put out by the EPA and the U.S. Fish and Wildlife Service. And now anytime somebody's trying to manage biology, wildlife, or trying to harvest anything, crops or trees, or trying to manage the land, the landscape, it's often best to know where your water is, where your wetlands are. And so it's cheaper. All these other programs benefit on top of deriving an accurate and up-to-date hydrography data set. And some of those other programs or products that you could develop on top of this river, the elevation derived, LiDAR derived stream center lines, you can create management boundaries for areas of concern, whether that be for fisheries or any other wildlife habitat or riparian area managements. You could characterize the extents of the wetlands. They vary. Wetlands and riparian areas they're not always just 30 feet. There are 30 or 50-foot buffer along a stream center line the entire route of the stream. They vary with the topography along the river. And so maybe you can create a variable with topography riparian area that would aid in management of multiple habitat and wildlife, flora and fauna techniques. And this is just one example of a stream network in the North Woods. We have some aspen growing that's showing in yellow. We have also some tamarack and black spruce swamps. And we have a LiDAR derived stream channel flowing through the center here in blue. And when we apply the riparian area, the variable with topographic riparian area assessment from LiDAR, we can get a polygon or a management boundary for where everything that would be defined as a wetland based on topography relative to the stream center line, is located. And so we can see from this image, it pretty well lines up. We're not seeing any aspens within our topographic riparian area. There's a little bit of yellow in the center bottom, but that is a tamarack black spruce swamp. But anyway, this is just one example of what you could derive on top of LiDAR derived hydrography.
Thank you, Tyler.
With that, I'll pass this back to Adam. He's going to have a little demo of interactive LiDAR layers.
I'll try this, Jim. I know we may be getting close to time here, so if you filter any questions, we can certainly do that.
Yeah, we're getting a little short on time, Adam, and just to let you know your audio is a little bit soft.
Okay. Can you see the new map on the screen?
Yes.
Okay. So if there are questions, Jim, feel free. I'm just going to jump through some of these in real data scenarios. So what we're looking at here is a stream power index that we were talking about for the DNR's eval model. I can start to turn on other data sets. This just helps drive home how your other departments can utilize this data. You can see how the stream power index correlates with that soil loss potential, or create a vulnerability index. And you can bring this into real world data sets. If you want to understand why we're seeing what we're seeing, you can see you're obviously going to have higher soil loss potential because we're in this 3D space. We're on the side of a hill. How are we going to use your slope ranges? So we can see the slope ranges drawing in here with our data. Again, real world scenario. We've got a build site that is not on the slope. that was built on the high point of the land. We've got this across the county-wide area. We can take a look at our depressions across the landscape. And all this can be brought in with your other geospatial data. So it's easy for a non-GISer to understand what it is they're looking at. I can see my depressions. I can zoom into the space. I can actually see the depression on the landscape of the map and see if that has any impacts on surrounding structures. Even with our building heights, I can quickly represent my highest and lowest points of buildings, in this case across an entire county. You can see my highest points of buildings are listed in blue. And for this application, I've given the heights, both real world as well as the relative height, and our minimum elevation on the landscape. And I can measure these back across from the shoreline. So some real quick things that you can do with your LiDAR data that you can provide back to the other departments in your office to realize more return on the investment that you made in getting that countywide LiDAR data.